will discuss about concentration process, right? So at the end of concentration, we will get concentrate. That is more important. And also we get another product, that is the tally. These are the two products after concentration. Suppose you are doing concentration, any kind of concentration you are doing. This is like you remember, slurry of fine, slurry of fine. Classification. Okay. So just before concentration, we do classification. Classification, we get a particular size, range of particles. That is known for concentration. And finally, concentration give you two products. One is your tannin, and one is your concentration. This basically we discard. This basically known for metal extraction. But nowadays, these tannins, we are not discarding. Lot of research are going on. Because we, if you remember, I told you once, we need circular economy, we need sustainability, so we cannot discharge the tannins in normal environment. If we discharge them, what is the problem? Maybe they contain heavy metals. So heavy metals will be washed away by rainwater, it will go to the groundwater pollution will be there. So we cannot discharge. They are very fine particles now. Tannins are also very fine. So they are easily leachable. When acid rain will be there or normal rain will be there, they will be easily leachable, and this leachable means they are soluble in the rainwater, and they will go to the groundwater and it will cause the groundwater pollution. So basically, tannin contains chromium, lead, arsenic, heavy metals, right? And also, what is the another issue of tannins? If you see, we cannot stop the metal extraction, mineral processing, right? We have to do mineral processing. So every year, lot of amount of tannins is generated per year. Some tons, some million tons of tannins is generated. If you store it somewhere, like I told you once, red mud in the Koraput region, you see, they are destroying the people, they are destroying the environment. So they are storing it for a long interval of time. Right? So if you store it for a long interval of time, it will damage the land also. You need a huge land, some acres of land is needed to store that. So that land will get damaged. You cannot grow any crop there. And if any failure will occur, suppose the dam wall will get failed, so it will go and spread everywhere. If there is nearby river, it will mix with nearby river. It may kill the animals if they get trapped in that, because mostly they are in form of slurry, liquid form. That's why it is called talling ponds. Don't get surprised if somebody will ask what is a talling pond. Pond means water, no, of course. So talling pond means tallings are stored in the form of ponds, in a dam, right? In form of liquid, right? So many things happen. In Muri once happened. I told you in Muri region. Muri is in Jharkhand. So that is belongs to Hindalco. So once the dam wall gets failed, and it sprayed through acres of land. That red mud got sprayed through acres of land. Some animals and some people got died. They got trapped in that. Because they are high toxic. Red mud is high toxic because the pH value is very high, around 12 or 12 to 13. So that my point was, tannins nowadays they are trying to utilize it. But the problem with tannins is what? Tannins are very fine. That is one of the issues. And the issue of tannin is the gangue amount is very high, but metallic value is very less. Right? But concentrate we know. Concentrate is the gangue amount will be very low, but metallic values will be very high. Right? So that's why the concentrate will be sent for metal extraction. So we'll discuss about. So now the point is, so this will be going for metal extraction. And you people know that there are three different routes of metal extraction. One is pyrometallurgy, one is hydrometallurgy, one is electrometallurgy. Right? So, if you see the conventional route of metal extraction, mostly they are pyrometallurgical process. Mostly. Nowadays also they are doing pyrometallurgical process. Right? But nowadays people have moved to hydro and electrons. Right? The point is, the concentrate which will take, that should be dewater first actually. It should not, in between that should be dewatering. In between there will be dewatering. That means you need to remove the water, of course. So after removing the water you will have fine particles, but those are solid fine particles. Okay. Let me give two examples. Aluminium and suppose iron extraction. Talking about the metal extraction. Extraction of aluminium, iron. Suppose extraction of magnesium also, or maybe zinc. Suppose I am talking about copper. See the metal extraction of aluminium, iron, magnesium, zinc and copper, right? But if you see extraction of aluminium, that is done by electrometallurgy process. And that process is called Hall-Heroult process. Okay. And in that case, we can directly use the fine concentrate. We don't have to make it into lumps. If you go to maybe you will go for your internship. Somebody will go for Hindalco, maybe some Vedanta or maybe Nalco. When we will go there and you will see how they are extracting aluminium. So they are actually using powder alumina, which is the main concentrate. That means the bauxite will be converted into powder alumina. That alumina will be gone for metal extraction, and those are in form of powder. So directly they are feeding the powder into the reactor. That is actually called electrolytic cell. And that process is electrometallurgy because they are using electricity there. You understand my point? But if you look into the extraction of iron, that you cannot charge fine concentrate directly into the reactor to produce iron. You have to make into lumps. A desirable size is essential. You cannot randomly feed any size. You need a desirable size, which is the feed size. Basically, there is a process called blast furnace iron making. You might have heard this one. Anyway, some people may go for internship to RSP, maybe you'll go to Tata Steel, you'll see this blast furnace, right, where the iron is extracted. So you need, what I told, you need fine concentrate here, but you need lump here. For magnesium also you need lump. Zinc also sometimes you need lump. Copper also, copper sometimes is directly charged fine, not lump. You have to extract copper out of copper sulfide, chalcopyrite. You will end up with fine particles of chalcopyrite. You can directly feed that fines into the reactor to extract copper. But if you want to extract iron, magnesium, zinc, you need to feed lumps. So, and the important point is, see, basically what I told, electrometallurgy basically requires fine particles directly, fine concentrate. Okay. Similarly, if you want to do hydrometallurgical extraction, there also we need fine particles, not lumps. Why? Can you tell me? Sorry? Easily soluble. Why easily soluble? You got my point? For electrometallurgical metal extraction, you need direct fines, concentrate. For hydro also, you need directly fines. You don't need lumps. Why it may be? Very good. Because fine particles have high surface area. If you compare two particles, one is finer, one is coarser. Finer particles have always high surface area. The number of atoms available on the surface will be more per unit volume of the material. Right? So that means reactivity is more, and in hydrometallurgy, we basically need what? Either acid or alkalis, or maybe sometimes water directly, like you have seen copper sulfate. You take copper sulfate and put it in water, it will become soluble. No need of anything, right? Only water is enough to dissolve it. But to dissolve any concentrate, basically we need acids, we need alkali, right? For example, let me give an example of Bayes process. Remember? So Bayes process, we are converting the bauxite into powders first. Then we are using NaOH, that is an alkali, concentrated alkali, right? So that the alumina will be soluble in that. So that means hydrometallurgy needs solubility. You need to dissolve something. To dissolve something, you need a reaction to happen. And if surface area will be more, reactivity will be more, solubility will be more, of course. You understand my point? So that's why in maximum hydrometallurgical process, we use fines directly. Fine concentrate, not lumps. Electrometallurgy also fine. But whenever you are going for pyrometallurgy, in maximum cases you need lumps. You cannot charge directly fines. You understand my point? This fine concentrate you cannot charge. Up to this it is okay, I think. So you need lumps for this, you need lumps for this, you need lumps. And the point is, there are two metals which are very important for human life or for the development of the country. What are those? Iron and aluminium, right? Iron and aluminium. Aluminium is extracted by electrometallurgy, forget about that. But iron, you need iron to make steel later. So to make iron, you need lumps anyhow. So that means the fine concentrate you need to convert into big size, acceptable size to the reactor. Let me give an example. For example, blast furnace. I told you the blast furnace iron. This one you will study in iron making subject again, but just an overview of blast furnace iron. Blast furnace iron making overview. So this is the reactor. So this is the reactor. So here actually what we are doing? We are supplying hot blast. Same, huh? Hot blast. Hot blast is nothing but what? This is oxygen and this hot air from the bottom of the furnace. So this is the furnace actually, blast furnace. So you can see from the blast, in the blast furnace, we are providing hot blast. Hot blast is nothing but oxygen and this air, hot air. We are providing hot air. It contains lot of oxygen actually, right? And blast means we are providing at very high velocity, maybe 250 to 300 meter per second. Such a high velocity we are providing hot. So that's why the name. Sometimes in interview they ask, what is why the blast furnace name is blast furnace? This is a very simple question. Sometimes they ask, why the blast furnace name is blast furnace? Because we are not doing any blasting actually. We are not exploding anything. But we are providing the hot air at a high velocity, that's why it is blasted. Okay. That's why the name is hot blast furnace. You can simply say blasting of hot air, hot oxygen enriched air. Or we are providing air at a very high velocity in hot condition. Okay, anyways you understand my point? So you can see, when we provide air with oxygen, what will happen? It cannot go down, of course, nothing is there at this end, it will go up like this, it will travel. So air will travel to the top. And I told you this air is having what? Oxygen mostly. And of course some nitrogen will be there. It is not pure oxygen, it is oxygen and nitrogen mostly. Okay. But from the top, what we are charging? Concentrate. iron ore concentrate we are charging from the top. But this concentrate will be in form of what I told? Lumps. Lumps. It may be lump iron ore, or it may be pellet, or it may be sinter. These are the three things we can charge, or mixture of them we can charge. So sinter is a lump, pellet is also a lump, and lump iron ore means lump iron ore. Okay. And if you remember, the concentrate is not pure form. Some gang will be still there, right? To remove that gang, we need a material that is called flux. That is called flux. So we need a flux, and basically we use dolomite or limestone. But the point is, nowadays we are not using limestone and dolomite. We are using flux pellets, flux sinters, you can say. Directly in that sinter, the flux will be there. Not separately we are charging. That is very interesting. I will tell you later. Then what we need, see, this concentrate of iron ore will be what? Fe2O3? Of course. Iron ore concentrate is nothing but Fe2O3 and some gang, silica and aluminum. And you want iron at the end. So you need a reducing agent, of course, to take out the oxygen from the Fe2O3. So you need O plus O. These are the what? Reducing agents. So these are the three materials you need to extract iron, right? One is iron ore concentrate, one is the reducing agent, one is the flux. So function of flux is what exactly? It will remove the gang. Function of reducing agent to remove the oxygen, and finally you will get molten iron and molten slag. You remember I told you two products are formed. In pyrometallurgical process, always two products are formed basically, and they are formed separate layers. Density of iron will be more, so it will remain in the bottom, and density of slag will be less, so it will remain on the top. If you mix them also, they will again separate into two layers because of difference in density and immiscibility. These are the two things always you have to remember. Slag and metals, they are immiscible and their density is also different. Okay. So finally, that means you will end up with this. Your slag will be there, your metal will be there. The metal means basically this is for pig iron, molten pig iron, and this is molten slag. So just see this process. From the top you are charging the solids. From the bottom you are charging what? Gas phase. Is it fine up to this? From the bottom you are charging hot blast, which is nothing but hot oxygen mostly. And it is going up. And from the top you are charging solid materials. Your iron ore concentrate, your flux, your coke, all are in solid form. So what will happen? They will descend down with time. So they will move. They will go down like this. They will go down. So this is the reason why the blast furnace is also called counter current reactor. Counter current means something is going down and something is going up. So they will interact at a time, right? A time will come, they will interact with each other. Opposite direction, right? Counter current means suppose someone is moving like this, someone is moving like so. This is counter current. Co-current means they are moving in same direction. Okay. Fine. This is called counter current reactor. That's why. So just imagine we have coke and coal also. That is nothing but the carbon. And hot air is also coming, which contain oxygen. So what will happen? Oxygen will react with carbon to form carbon dioxide first. So carbon plus, I am not balancing it, I am just simply writing. It will form CO2, of course. I think ma'am have already started about Ellingham diagram. You know, I also explained in one class, I remember. So in Ellingham diagram, if you see, remember, there is a line, carbon monoxide line. monoxide line, right? This one is, if you remember, this one is what? Temperature axis in degree centigrade. And this one is delta G naught. Always. Not delta G naught. In interview sometimes they ask what is the y-axis and what is the x-axis in case of Agglomeeation diagram. Simple question. But many people say that is delta G, but that is wrong. It is delta G naught. Delta G naught means standard free energy change. Or standard gives free energy of change. Or for this you can write standard free energy change or standard free energy of formation of any compound. Right. Okay, anyway, so this is carbon monoxide line, okay? And carbon dioxide line will be like this. But all metal oxide line will be like this, if you remember. Metal oxide line. They are moving upward. And this line is moving downward. So what exactly it means? That means with increasing in the temperature, see, temperature is rising this direction and metal oxide line are moving like this. So that means, and if you remember delta G naught starts from 0. This is a very interesting. From the top it starts from 0 and towards bottom it becomes more negative. Otherwise you will get confused. Maximum people will think it starts from 0 and it will go up, positive direction. But it is not. 0 starts from here and it will become more negative. Negative. Suppose 100, 200, 300, 400, 600, whatever. Like that. Negative everything. And we know a simple concept. More is the negative delta G naught value, that particular compound is more stable. So that's why Agglomeeation diagram is also called stability diagram. It talks about stability of oxides. It talks about stability of sulfides. It talks about stability of chlorides. So Agglomeeation diagram is not only for oxides. It is for chlorides. It is for sulfides. Whatever the ore is available, it talks about their stability. You understand my point? So that means more you go down, stability of compounds or oxides will be more. They are more stable. You cannot decompose it. Suppose I am talking about Fe2O3. If Fe2O3 is more stable, you cannot decompose it into Fe and oxygen. It is not possible. You understand my point, right? Similarly, you can see this line is going downward with rising temperature, but metal oxide line is moving upward. So which one is more stable with temperature? And which one become less stable with temperature? Metal oxides become less stable. Very good. Because they are moving upward, no? Right? So upward they are moving means you are moving toward positive direction. Okay. But carbon monoxide line is moving downward with temperature. Temperature is increasing, carbon monoxide line is going down. So the negative value is increasing for carbon monoxide. So more is the temperature, more is the stability of carbon monoxide. So carbon monoxide will remain there in the furnace if carbon will be there and oxygen will be there. Listen carefully, this is very interesting point. If in the furnace carbon is there, which may be coke or coal, solid carbon, and oxygen will be there. So, and temperature is very high. So CO2 is not stable. CO is stable. So CO2 will become CO then later because of its stability. You understood up to this? Fine. So see the first reaction I told you, this reaction will happen because oxygen is coming and reacting with carbon. This is coke or coal to form CO2. Then what happens? Then again CO2 will react with carbon to form carbon monoxide gas. These are gases. This is solid. This is also solid. So finally you are getting what? Hot carbon monoxide gases. And this hot carbon monoxide gas is moving upward, I told. They will move upward and your iron ore concentrate is moving downward. They will interact and reduction will happen. Fine. So carbon monoxide plus Fe2O3 will give you Fe. I am directly writing the final reaction, Fe plus CO. Okay, so you get what? Molten Fe and a gaseous product, that is CO2. These are the two products you got. You understand the point? Up to this? Is it okay or? Fine, the final reaction will be, you can write like Fe2O3 plus carbon monoxide. You can get Fe and CO. So this is your free layer and also flux will be there. So your slag will also form because flux is also there. Flux. Okay, can you tell me what kind of slag will form? What is the composition? It will be having alumina, it will be having silica, and it will be having lime, CaO. These are the three components. Like you can say Al2O3 into SiO2 into what? CaO. So this is your slag, this is your flux material, and this is your gang material. They become slag. Is it fine? Because you remember the iron ore main gang is silica and alumina. You cannot remove all silica and alumina during mineral processing. Some will be there. So that can be removed during metal extraction. These are very important points you should remember. Up to this it is clear, I guess, right? So now we'll move to. Okay, yeah. You understand the point why this is happening? Because carbon monoxide stability is increasing with temperature, but metal oxide stability is decreasing. And they're meeting at a junction. There is a crossover. See, all metal oxide line is cut by this carbon monoxide line. So at that point is the equilibrium temperature. If you maintain a temperature above that, then reduction is possible. Fine. Suppose this is the metal oxide line. This is moving like this. Carbon monoxide line is moving like this. So this is the junction where they are cutting. So if you want to reduce this metal oxide by carbon monoxide or by carbon, you need to maintain a temperature above this, like this. This temperature is fine. You can reduce it. But if you maintain a temperature here, this temperature, it is not possible. So that is very interesting about Ellingham diagram. So Ellingham diagram will tell you at what temperature reduction is possible by carbon. Right. And if you remember, I told you also metallothermic reduction. Well, I will not go into that right now. Anyway, it is fine up to you. Okay. So now, yeah. So now the point is this iron ore concentrate. You need lump, I told, lump ore directly, and you need or filter, or you need pellets mostly. These are the iron ore concentrate which you feed into the furnace. See, this is very interesting. Iron ore lump. Iron ore lump means you are doing mineral processing, but not so extensively. My point is, suppose you have high grade iron ore. Listen carefully. You have high grade iron ore, right? High grade iron ore means what? The gangue content is very minimum, but metallic values is very high. That is high grade iron ore, right? So that means you don't need more liberation. I told you. Why we do mineral processing? Because of two things. One is liberation, one is separation. Right? Liberation is the first thing. You need to liberate means you need to unlock the gangue and valuable metals. But it is already high grade. Gangue amount is very less. So if you do only crushing, then you can remove them easily. Just by doing crushing, you don't have to go for grinding. Because once you start grinding, it becomes microns. But once you do crushing only, suppose primary crushing, still you have big size, lump size of iron ore directly. And it is high grade iron ore. So you can directly feed into the furnace. There is no issue. But the problem will come if iron ore is low grade or medium grade. You understand my point? So if you are dealing with medium grade iron ore, then you need crushing, then you need also grinding. Because you need more liberation, more unlocking, right, to separate them later. If it is low grade, then you need more extensive grinding. Very, very fine grinding you need, right? You understood to separate them finally. So finally you end up with very fine ores. Then you need to do either sintering process, this is called sintering process or sintering technique, or you need to do pelletisation. Okay, I'm not writing here better. So you need to get sinter, you need to do sintering. This technique is called sintering technique. And this is called pelletisation. Pelletisation. So these are nothing but agglomeration technique. And agglomeration technique means fine shoot converted into lumps. And we'll discuss about this sintering and pelletisation in details. Is it okay after this? So now, okay, so I'll try different techniques. techniques of agglomeration or agglomeration process, whatever you can write. So first one I can write liquating, one is normalizing, one is extrusion, and the most important is sintering, and finally pelletisation. So this is industrially used, this process is industrially used, but we are not using this, we are not using this, we are not using this nowadays. These are the conventional, but we are not using nowadays. Mostly we do sintering and pelletisation. I think you worked on pelletisation, right? You've seen that. These are the different techniques for converting fine into lumps. Simple. Okay. But in industry we choose this one and this one because they have more advantage. Compared to these things, they have more advantages. That's why we choose either sinter or pellets. Fine. Now I will talk about sintering. Sintering, then what exactly sintering means? See, you have very fine concentrates, solid concentrates. They are very fine, right? You simply do what? You take it to high temperature. For example, in case of fine iron ore concentrate, we take it to 1000 to 1300 degrees centigrade, in that range. All fine iron ore concentrate are together, and you are taking it at a temperature of 1000 to 1300 degrees centigrade. So what will happen? So every solid substance has a melting point. So if you check the melting point of iron ore, it may be how much? Can you check? Maybe around 1450 to 1500 nearly. Can you check it? Just melting point of 1539 is the melting point of pure iron, but it is iron ore concentrate oxides. Can you check? Melting point of iron oxide Fe2O3. Maybe around same 1400 to 1500. 1350 to 1500. It is range. Very good. So that's, see why I told we need to take it to 1000 to 1300, not above that. And we got that the melting point of this fine iron ore concentrate is how much? 1350 to 1500, in that range. So that means we are taking the fine iron ore in below that temperature, below the melting temperature, and near to the melting temperature, but not at exactly melting temperature. So that technically called incipient fusion temperature. So that means you take fine iron ore concentrate and heat it to this temperature, fusion temperature, that is basically 1000 degrees centigrade to 1300 maximum. This is the temperature range. So finally you will end up with lump, a big size lump. It will become a single piece. Entire fines become a single piece, kind of a block or a big size stone, you can say, whatever. And technical, that is called incipient fusion temperature, means the temperature just below the melting point. That is called incipient fusion temperature. Fusion means you are completely melting. Incipient means just below the melting point. Okay, fine. So this is one of the way to make lump out of fines. But what do you think? And for blast furnace feed, if you want to feed a sinter into the blast furnace as a feed material, there is a particular size range. What is that size range? 10 mm to 30 mm. So I told you now, you cannot charge any feed size of material into the blast furnace. There should be acceptable size. That furnace required that particular feed size. You cannot charge less than that, or you cannot charge more than that. So what is for sinter? I told what is the size? If you want to feed sinter for blast furnace operation, the size will be 10 mm to basically 30 mm or some say 10 mm to 40 mm max. 10 mm to 40 mm. But if I write minus 10 mm, can I feed it? My size is minus 10 mm. Can I feed it? No. Minus means if you pass through the screen, it will pass again through the screen. It will not remain on the screen. Minus now. Today you have lab exam, right? Sir will ask you this question. What is minus and plus? I told you already, when you are doing screening, one will be oversized, one will be undersized. Undersized is minus, oversized is plus. So plus means it will stay on the screen, minus will pass away. Simple. I told you about mesh size, mesh number. Sir will going to ask you same question. What is mesh size? What is mesh number? Okay, anyway. So this is the acceptable size, right? And you remember, fine iron ore concentrate size will be how much? If it is medium grade or something, how much it will be? Maybe 50 micrometer, 200 micrometer maybe. See, so much fine becoming big size. But what I told, we are getting a big size component, not this size. We are getting a big size like this much. Just imagine this size of lump, single lump. So what we need to do? We need to crush it. We need to again crush it and pass through a screen. The particles which are above 10 mm, you directly feed it. The particles are below 10 mm, you just again recycle it into the process. You need crushing of course. But in case of pelletisation, we directly get the required feed size. We don't have to break it or crush it in form of balls. I will discuss that coming. Is it up to this point? So of course this will need crushing. Then what? Screening. Then you get the acceptable size. The final size will be recycled and the required size will be fed into the furnace. Okay, up to this it is fine. Now I talk about sintering process exactly. That machine used to do sintering in steel plant. You are going to do internship in JSW maybe or maybe RSP, maybe Tata Steel. You will gonna see this sintering machine. That is very interesting. But that area is very polluted. The moment you go, you will see. So what is that machine called? Lloyd. Sintering machine. Lloyd sintering machine. So how the machine looks basically? Right. So it will be having this is one end and this will be another end. So what is this basically? What you understood? This is the roller and here is the roller. And this is your charging end. And this is discharging. Here there will be ignition hood. So this is your ignition hood. A burner, kind of. Ignition hood means a burner will be there. And there will be a charging port. So it will be what is there? Iron oxide fines will be there. In the charging end, you need to feed iron oxide fines. But I told you to do sintering, you need temperature. So who will provide you temperature? So we add some nut coke. That is called nut coke. So it will be also having nut coke means, see, in the blast furnace we are also providing coke, and in sintering process also we are providing coke. But this coke is called nut coke. Nut coke means the size is small. But in the blast furnace the size of the coke we provide is more, bigger size. Okay. So this is called nut coke. And I told you one another important point. Nowadays we are not providing blast furnace this limestone or this dolomite directly. We are incorporating into the sinter itself. That means we are directly providing sinter, which will be having your iron ore as well as flux. They will be together. We are not separately providing. What is the reason actually? Okay, in one line I can say energy consumption will be less. The point is, if you provide limestone and dolomite directly into the furnace, then what will happen? You remember I told you there is a process called calcination. Right? The limestone will undergo calcination, the dolomite will undergo calcination. That is nothing but thermal decomposition process. And that process is endo or exo? Exothermic or endothermic? Exo. Who is saying exo? Thermal decomposition is happening. You want to decompose the compound. That is actually endothermic. Endothermic means they need temperature, they need energy. So in the blast furnace they will consume the energy during calcination. We don't want that. We want energy for melting, we want energy for reduction. Right? But if you provide energy, if you consume energy for calcination, so you are losing the energy, no? The cost of process will be more. Right? Or maybe the metal will get freeze inside the furnace, maybe. Chances that. So that's why we are incorporating the flux in the sinter itself. So what is the other point I can write? What? Dolomite? I like dolomite. With a flux. So these three things will be there in the charge. And that is called charge mix. These are all called charge mix. Charge mix. And this is in form of what I mean? Granules, actually, in granule form. Granular form. Granular form means what exactly they are doing? They are mixing it, then they are providing some water molecules on it. So they will become small granules. Not very big size, small granules. Why? Can you think of it? Okay, I will ask that question later. Anyway, so there is a ignition hood. Ignition hood means there will be a burner. Burner function is what? It will provide you heat energy. Burner means it is a fuel burner. You are providing fuel and it is burning. See? And also, let me change the color. This will be having tray kind of system. Tray kind of system will be there. Kind of tray, not exactly, but kind of tray kind of system will be there. And but they have openings, no? But they have openings at the bottom of the tray. Small openings. And this is basically called endless band. Endless band of pellet. Those are actually, just imagine a tray, and those tray is having. Can I use your cell phone?
Yes, sir.
So just imagine there is a tray kind of thing, like this, fine, and bottom of the tray is having holes, like string. It is not so big holes, small holes will be there, right? So many trays will be there. And this is, I wrote endless band. Endless band means it is endless, no? It is going like this and coming again like this, again going like this, again coming like this and like this. It is moving. Okay, from this direction, this direction. Like, just imagine this is the railway track and your bogie is moving. Who is carrying the material from charging to discharging it. And that bogie is again coming and again taking the charge and moving down. But this will go at a very slow rate, not very fast. So up to this it is fine. Thank you.
Welcome.
So now you have, these are what? Suction fan. So these are suction fan. Suction fan, or basically called wind box. Wind box. So I am preparing you for industrial visit. The moment you will go there, you will understand what is going on. You can answer them, sir, this is that, we know this from the class. Anyways, see, wind box means those are actually fans, and those fans are actually moving like this, downward, like this fans, right? See, these are the fans, same big size fans will be there, but they are rotating at a very high velocity, right? So they are actually sucking the air. If fan will move like this, so it will suck the air from the top to the bottom, of course. But if the fan will move like this, it will take away the air from bottom to top, right? So basically, that means, and they have holes. I told you that this tray has holes, and this is your air, ambient air, right? This is ambient air. So what will happen? Air will flow in this direction. Okay. So air will flow. This is the flow of air. That's why this technique is also called down draught sintering. Down draught sintering. Down draught means the air is sucking from the top towards bottom. Up draught means air will be sucked from bottom to top. This is called down draught sintering. Down draught sintering machine. Air will be sucked from the top to the bottom because this is normal atmospheric air and fans are moving at a very high velocity, so air will be sucked, but sucked through this tray. And tray has what? Materials. Tray is having materials of whatever materials you are feeding. So tray will be having the material. Maybe white color. So these are the these are the bed. See, now the main, I'll start the discussion here. Let's see. So one tray is coming, it will receive the charge, mix. They are in form of granules. They have nut coke, they have flux, they have fine aeronautes, right? So the moment it will reach here, what is there? Burner is there? Burner. So burner will do what? It will start combustion of the top layer. The top layer will ignite because coke is there. No? Coke will burn. Iron ore will not burn. Flux will not burn, but the coke will burn. Only the top layer because that is basically of some thickness. Right? So one combustion will start. This leg will migrate to this direction. Now the fans are there. The air will suck from the top and it will pass through this. So this bed is actually permeable bed. We call it permeable because it is allowing the air to pass through it. So what will happen? What do you think? This combustion zone will migrate to the next layer. Then again it will migrate to the next layer. Slowly, when it is moving down, it is going like this. Suction is continuously happening. So the combustion layer which is at the top will migrate to the next layer, to the next layer, to the next. Finally it will reach to the bottom layer. That we want. Why we want combustion? Because we want temperature of around 1000 to 1300, I told. That is called incipient fusion temperature. So all the fine iron ore become a single lump. So finally what will happen is this will come and this tray will reverse. So this will fall down. Whatever the sinter forms, that will fall down. That will be cooled, then that will be crushed, that will be screened, and the material will be sent to the blast furnace. Fine, again that empty tray will come and again it will receive the fresh material. Right? So lot of empty trays are there. No? So they will go and like this. So that's why that is discharging it. That means you charge fines here, you will get lump here. Your lump will be discharged. your fines will be charged. Is it fine? And what is that for BTB? One. So it is fine. If you want, you can take a photo of this. Okay, how the combustion zone will be? Just imagine these are layers. Huh? What is this? I told this is sinter mix bed. This is sinter mix bed. So I told the top layer is ignited first. The moment it will come below the ignition, then suction of air is happening. Air is sucking down. So this combustion zone will move to this. Then it will move to this and move to this, move to this. But continuous air is flowing. So what happened to the when the combustion zone migrate to the third layer, for example? What happened to the first zone? It will cool down. Very good. It will cool down. Because fresh air is coming. When all the carbon will burn out, it will cool down. So similarly, combustion zone is migrating, cooling is also happening. Right. And when this combustion zone will reach to this point, then sintering is done. That is called burn through point. BTP. Yeah, burn through point. And there is also an updraft sintering machine that is basically used for sulfide ore. If you want to convert sulfide fine concentrate to lump, then you can use updraft sintering machine. Just opposite. The air should move from bottom to top. And that there is a reason behind that. Can you think of it? What may be the reason? So it's a very light. Huh? I told you, there are two types of sintering machine. One is downdraft, this one is downdraft. Downdraft means the air will be sucked from the top to bottom. Updraft means the air will move from bottom to top. And for sulfide ore, basically we go for updraft one. And for oxide ores, we go for downdraft. You have studied roasting already, no?
Yeah. Sulfide hydrophobic.
During roasting, what happens basically? Sometimes we use oxygen in roasting or air. And what happened during that? Roasting is an autogeneous process. Because sulfides are combustible. If you take the sulfide to high temperature, it will burn automatically. It will form SO2 and it will release a lot of heat. Automatically. You don't need any kind of fuel. But for oxide, you need a fuel, that is coke. For sulfide ore, we don't need any kind of fuel. So what basically we do? We charge a small single layer first and we ignite it. It will automatically ignite. From the top we charge next layer, next layer, next layer, and it will move. But air will move from bottom to top. The bottom layer is ignited now. It can move to the top. So bottom layer will first cool, but the combustion zone will move to top. Automatically it will ignite. You don't need any kind of coke there. Sulfide ores are highly combustible because it contains sulfur. Right? Sulfur S plus O2 will become SO2 and it will release heat automatically. So most of the roasting process are autogeneous process, if you see. But the condition is it should be dried form. If it contains a lot of moisture, it is very difficult to ignite it. Dried sulfide ores are combustible. Anyways, you understood this part. This is called white load sintering machine and this is the working, how it works. Okay, I'll continue in the next class.